For most of modern history, we believed we understood the size of our cosmic home. Textbooks said it. Diagrams confirmed it. Animations repeated it endlessly. The Milky Way, our galaxy, was presented as a tidy spiral about 100,000 light-years wide. That number felt solid, unquestioned, almost permanent. But it was wrong. Not slightly wrong. Not outdated by a minor correction. Fundamentally wrong. New observations now show that the Milky Way is at least twice as large as we were taught, stretching far beyond the boundaries we confidently drew for decades. For nearly 70 years, science underestimated the scale of the very structure we live inside. This is not a small adjustment. It is a rewriting of our cosmic address. Everything built on the old measurement, how we calculate mass, how we predict galactic collisions, how we estimate the number of stars and planets, suddenly shifts. The unsettling part is not just that the number changed, but that it took so long to notice. We trusted the maps because they were familiar. We repeated the measurements because they seemed precise. Yet all this time, we were standing inside something far larger than we imagined, mistaking the bright center for the whole. The discovery forces a humbling realization. Even in our own galaxy, the place we call home, we were measuring only a fraction of the truth. Understanding why we got the Milky Way so wrong requires confronting a simple but deeply misleading problem. We are trying to measure our own galaxy from the inside. Unlike distant galaxies that appear as complete shapes against the blackness of space, the Milky Way surrounds us in every direction. There is no vantage point where we can step back and see its full outline. We are embedded inside one of its spiral arms, roughly 26,000 light-years from the center, looking through dense fields of stars, clouds of gas, and vast curtains of cosmic dust. This position creates a powerful observer bias. Imagine standing in the middle of a massive city and trying to determine its true size by sight alone. Buildings block your view. Streets curve away. The skyline disappears into haze. You might confidently draw a boundary where the lights seem to end, even though the city continues far beyond what you can see. For decades, astronomers faced the same problem. Early measurements relied on counting the brightest stars visible in different directions. Where those stars thinned out, scientists assumed the galaxy ended. That apparent thinning became the official edge. The number settled around 100,000 light-years, not because the galaxy truly stopped there, but because our instruments stopped seeing clearly. Dust played a major role in this illusion. Thick clouds of interstellar dust absorb and scatter visible light, hiding vast regions of the galaxy from optical telescopes. Entire sections of the Milky Way, including much of its center and outer reaches, were effectively invisible. Even worse, the galaxy does not end abruptly. Stellar density fades gradually. Stars become fewer, dimmer, more spread out. There is no sharp boundary, no wall, no sudden drop to nothing. The old methods mistook this slow fading for a hard edge. Perspective compounded the error. Brighter stars are easier to detect, so maps favored the luminous inner regions while overlooking faint stars drifting farther out. These faint populations still belong to the galaxy, but they blend into the background unless you know exactly how to look for them. For a long time, astronomers were not careless. They were limited. They measured what they could see and assumed the unseen was insignificant. Only now are we realizing that the unseen was not empty space at all, but most of the galaxy itself. As astronomers pushed deeper into the problem, another uncomfortable truth emerged. Galaxies do not have clean edges. There is no precise point where a galaxy suddenly stops and empty space begins. The Milky Way does not end like a disk or a wall. It dissolves. Star by star, the population thins, stretches, and fades into the darkness. Early measurements assumed an edge because they needed one. Science likes boundaries, numbers, clear limits. But nature does not always cooperate. The mistake was not only assuming a boundary existed, but assuming it coincided with what we could easily see. The brightest stars form a dense, glowing core and well-defined spiral arms. Beyond that region, stars become faint and sparse, difficult to detect with older instruments. Those outer stars were largely ignored, dismissed as background or statistical noise. Yet they still orbit the galaxy. They are still part of it. More importantly, stars are only a small fraction of what makes a galaxy a galaxy. As measurements of stellar motion improved, scientists noticed something deeply unsettling. Stars far from the galactic center were moving too fast. According to the visible mass alone, they should not be bound at all. They should escape into intergalactic space. Something unseen was holding them in place. That something was dark matter. Invisible, undetectable by light, but unmistakable through gravity. Dark matter forms an enormous halo around the Milky Way, extending far beyond the visible stars. While the luminous disk might fade, the gravitational influence does not. This halo outweighs all visible matter combined and defines the galaxy's true reach. Early maps missed it entirely because dark matter cannot be photographed, but its effects are undeniable. It bends light, shapes orbits, and anchors stars that would otherwise drift away. Once this invisible mass is accounted for, the idea of a sharp galactic edge collapses completely. The Milky Way is not defined by where stars stop glowing, but by how far its gravity extends into space. Once astronomers accepted that the Milky Way had no clear edge and that invisible mass dominated its structure, a new question followed naturally. How far does the galaxy's gravity truly reach? Answering that question required a kind of evidence that could not be hidden by dust, distance, or faint starlight. That evidence came from stellar streams. Stellar streams are long, delicate rivers of stars stretching across the sky, remnants of smaller galaxies and star clusters that wandered too close to the Milky Way in the distant past. When those smaller systems approached, our galaxy's gravity pulled them apart. Their stars did not disappear. Instead, they were stretched into elongated trails that continue to orbit the Milky Way long after their original homes were destroyed. These streams behave like cosmic test particles. Each star in a stream follows a path determined almost entirely by the galaxy's total gravitational pull, not just the visible stars, but all mass, including dark matter. That makes stellar streams extraordinarily valuable. They trace the shape, strength, and extent of the Milky Way's gravitational field with remarkable honesty. Unlike individual stars, which can have complex histories, stellar streams move as coherent structures. Their paths preserve information about the forces acting on them over billions of years. When astronomers began mapping these streams in detail, the results were startling. Many of them extended far beyond the region where textbooks said the galaxy should end. The Sagittarius stream, one of the most famous, wraps around the Milky Way like a ribbon around a gift, looping through space multiple times. Its stars orbit at distances far greater than 100,000 light-years from the center. According to older models, this should not have been possible. If the galaxy truly ended where we thought it did, the stream would not stay bound. Yet it clearly does. And Sagittarius was not alone. As surveys improved, more streams appeared. The GD1 stream, thin and sharply defined, traced a graceful arc through the outer halo. Other streams emerged, fainter but unmistakable, stretching tens and then hundreds of thousands of light-years outward. Each one told the same story. The Milky Way's gravity was still dominant far beyond the visible disk. The implication was unavoidable. The galaxy was not merely slightly larger than expected, it was dramatically larger. Stellar streams revealed that earlier measurements had captured only the bright skeleton of the Milky Way, not its full body. For decades, these streams went unnoticed or were dismissed as background features. They were faint, diffuse, and difficult to separate from the general stellar population. Without precise motion data, they blended into the noise. That changed with modern instruments capable of measuring stellar positions and velocities with unprecedented accuracy. Once astronomers could see how stars moved, the streams stood out clearly. Their members shared common motions, flowing together through space like schools of fish. This motion-based approach bypassed many of the limitations that plagued earlier methods. Dust could block light, but it could not hide gravity. Distance could dim stars, but it could not erase their orbital paths. Stellar streams turned the Milky Way into a crime scene, with each stream acting as preserved evidence of past encounters. And the evidence pointed outward, again and again. Some streams orbited at distances approaching 200,000 light-years. Others hinted at even greater reaches. The farther scientists traced them, the clearer it became that the galaxy's influence did not fade where tradition said it should. Instead, it extended into regions once labeled intergalactic space. These findings forced a fundamental reassessment of what it even means to belong to a galaxy. If a star orbits the Milky Way, responding to its gravity, then it is part of the Milky Way, regardless of how faint or distant it appears. By that definition, the galaxy grew immensely overnight. Stellar streams also removed much of the guesswork from size estimates. Previous methods relied heavily on assumptions about where star density dropped below some threshold. Streams required no such assumptions. Their paths were dictated by physics alone. Measure the stream's trajectory and speed, and you directly measure the gravitational field shaping it. There was no need to decide where the galaxy should end. The streams showed where gravity still ruled, and gravity kept ruling far beyond expectations. As multiple streams were mapped and compared, they converged on similar conclusions. Models that assumed a 100,000 light-year galaxy failed to reproduce the observed stream paths. Only much larger models fit the data. The Milky Way had to be extended to nearly 200,000 light-years in diameter, at minimum, to account for what the streams were doing. Some models pushed the boundary even farther. This was not a single controversial result. Independent teams, using different data sets and methods, reached the same conclusion. Stellar streams were quietly but relentlessly rewriting the map of our galaxy. The implications went beyond size alone. Streams also revealed the distribution of dark matter within the halo. Subtle bends and distortions in stream paths hinted at variations in the gravitational field, suggesting that dark matter was not perfectly smooth. In some cases, streams appeared kinked or warped, as if tugged by invisible clumps. These features offered rare clues about the structure of dark matter itself. The Milky Way's halo was not just large, it was complex. But for the question of size, the message was already clear. The galaxy's edge, if such a thing could be defined, lay far beyond the visible stars. What we once called the outskirts were merely the inner regions of a much larger system. Stellar streams provided the first clean, unavoidable proof that the Milky Way had been underestimated on a grand scale. They transformed abstract suspicions into measurable reality. Each new stream added confidence. Each additional orbit traced in the outer halo pushed the boundary outward. By the time enough streams were mapped, the old picture was no longer defensible. The Milky Way was not a medium-sized spiral with a neat boundary. It was a sprawling gravitational giant, extending deep into space, its true form hidden not by mystery, but by the limits of our previous tools. The streams had been there all along, quietly circling, waiting for us to learn how to see them. And as astronomers followed these stellar rivers farther and farther out, something even more unsettling emerged. Some streams did not simply skirt the outskirts of the galaxy. They occupied regions that had long been assumed to lie beyond it. According to older definitions, these stars should have been wandering freely through intergalactic space. Instead, their motions showed clear allegiance to the Milky Way. They curved, slowed, and accelerated in ways that only made sense if they were still deep within its gravitational grip. This forced scientists to confront an uncomfortable realization. Much of what we once labeled outside the galaxy was not outside at all. It was simply territory we had failed to recognize. One stream in particular sharpened this debate. The so-called orphan stream earned its name because astronomers could not initially identify the galaxy it came from. It orbits at such extreme distances that, for years, researchers argued over whether it even belonged to the Milky Way. New measurements settled the question. Its trajectory is shaped unmistakably by our galaxy's mass. If the orphan stream is part of the Milky Way, then the Milky Way must extend at least that far. There was no way around it. Each confirmed stream pushed the boundary outward in increments that seemed small on paper, but enormous in reality. 10,000 light-years here, 20,000 there. Over time, these additions stacked up until the cumulative change became impossible to ignore. The galaxy did not suddenly double in size. Our understanding of it did. Stellar streams also solved a deeper philosophical problem that had haunted astronomers for decades. How do you define the edge of something that fades gradually? Traditional definitions relied on brightness, star density, or visible structure. Streams ignored all of that. They cared only about gravity. If a stream remained bound, the galaxy extended to include it. If it drifted away, the galaxy did not. This criterion was brutally simple and physically grounded. It replaced subjective thresholds with measurable dynamics. When researchers applied this logic consistently, the result was clear. The Milky Way's effective radius expanded to roughly 200,000 light-years, possibly more. Beyond that distance, streams became rarer, orbits less certain, and gravity finally began to loosen its grip. But even here, the boundary was fuzzy. Some stars lingered near escape velocity, barely bound, skating along the edge of freedom. Their existence suggested that the galaxy's influence did not end cleanly, even at 200,000 light-years. Instead, it tapered off slowly, like a gravitational fog thinning into the void. This is why stellar streams matter so deeply. They do not just revise a number in a textbook. They redefine what a galaxy is. The Milky Way is not a glowing disk surrounded by empty space. It is a vast gravitational domain built largely of invisible matter, stitched together by the orbits of stars that remember where gravity once pulled them. Stellar streams are those memories made visible. They are the reason astronomers can say, with confidence rather than assumption, that our galaxy is far larger than we were taught. And they are only the beginning, because every new stream discovered adds another thread to a picture that is still being woven. Once stellar streams revealed how far the Milky Way's gravity truly extends, the conversation shifted from stars to the invisible structure controlling them. The streams did not merely suggest a larger galaxy. They demanded an explanation for the immense gravitational pull holding those distant stars in orbit. That explanation is the dark matter halo. Visible stars, gas, and dust make up only a small fraction of the Milky Way's mass. For every unit of ordinary matter we can see, there are roughly 10 units of dark matter we cannot. This invisible component dominates the galaxy, shaping its size, structure, and behavior. Without it, the Milky Way would not exist in its current form. Stars in the outer regions would drift away, streams would unravel, and the galaxy would slowly dissolve. Dark matter acts as the hidden scaffolding, the gravitational glue binding everything together. To understand the true size of the Milky Way, astronomers had to stop thinking in terms of light and start thinking in terms of gravity. This led to the adoption of a more physically meaningful boundary known as the virial radius. Rather than asking where stars stop glowing, the virial radius asks a different question. How far out does material remain gravitationally bound to the galaxy? Inside this radius, stars, gas, and dark matter orbit together as a coherent system. Beyond it, gravity weakens enough that objects can escape and join the wider cosmic environment. For the Milky Way, this radius turned out to be far larger than anyone expected. Early estimates placed it near 100,000 light-years, mirroring the visible disk. But stellar streams and satellite galaxy motions quickly invalidated that number. Revised calculations pushed the virial radius outward to roughly 200,000 light-years, and in some models, even farther. This realization reframed the galaxy's structure entirely. The visible Milky Way, with its glowing spiral arms and bright core, is only the tip of a much larger system. A useful analogy is an iceberg floating in the ocean. The part above water is what we see: stars, nebulae, and dust lanes. But beneath the surface lies a massive body of ice, far larger and heavier than the visible portion. Dark matter is that submerged mass. The true Milky Way includes both the luminous tip and the vast, unseen bulk below. When astronomers account for this hidden structure, the galaxy's dimensions expand dramatically. The dark matter halo is not a thin shell. It is a diffuse, roughly spherical cloud extending far beyond the disk in every direction. Its density is highest near the center and gradually decreases outward, with no sharp cutoff. This gradual fade is why defining an exact edge remains difficult. Depending on how conservative the definition is, the Milky Way's halo may extend well beyond the virial radius. Some models suggest the influence of the halo reaches 300,000 light-years. Others push the estimate to 400,000 or more. At these distances, dark matter becomes extremely diffuse, but it does not vanish. Gravity weakens, yet it remains measurable. Satellite galaxies orbit within this halo, their paths revealing how mass is distributed far from the galactic center. Gravitational lensing adds further evidence. Light from distant galaxies bends slightly as it passes through the Milky Way's halo, betraying the presence of mass where no stars exist. These subtle distortions confirm that the galaxy's influence stretches far into space. The implication is profound. The Milky Way is not a neatly bounded object drifting in emptiness. It is a massive gravitational domain occupying a region of space far larger than its visible appearance suggests. Much of what we once called intergalactic space is, in reality, still under the Milky Way's control. The galaxy's true size depends not on brightness, but on gravity. And gravity tells a very different story. When the dark matter halo is fully considered, the Milky Way may span several 100,000 light-years from edge to edge. The number remains uncertain, not because the idea is wrong, but because the halo fades so gradually that any boundary is necessarily approximate. What is no longer in doubt is the scale. The galaxy we inhabit is vastly larger, heavier, and more complex than the familiar spiral image suggests. Stellar streams showed us the reach of gravity. Dark matter explains why that reach exists. Together, they reveal a Milky Way that is not merely bigger than we thought, but fundamentally different in nature, a luminous island embedded within a vast ocean of invisible mass. Once the dark matter halo entered the picture, astronomers gained a powerful new way to test the Milky Way's true mass: its satellite galaxies. Unlike individual stars, satellite galaxies are large, coherent systems whose motions respond to the full gravitational pull of the Milky Way. They are not subtle indicators. They are heavy, slow-moving probes that trace the strength of the galaxy's gravity far from its center. If the Milky Way were as small and light as earlier models suggested, many of these satellites should not be bound to it at all. Yet they are, and their orbits tell a very different story. The most famous satellites are the large and small Magellanic Clouds, visible to the naked eye from the southern hemisphere as hazy patches of light. For centuries, they were treated as nearby neighbors, possibly passing visitors. The Large Magellanic Cloud alone contains tens of billions of stars, making it a substantial galaxy in its own right. Its current distance, roughly 160,000 light-years from the Milky Way's center, places it well beyond the old textbook boundary. According to earlier mass estimates, the Milky Way's gravity should not be strong enough to keep such a massive object bound at that distance. And yet, the Magellanic Clouds are clearly interacting with our galaxy. Streams of gas are being pulled from them. Their motions curve in ways that only make sense if they are gravitationally trapped. This alone hinted that the Milky Way was far more massive than assumed. As astronomers tracked the precise motion of the Magellanic Clouds, the numbers became unavoidable. Their orbital speeds were too high. For an object that far out to remain bound, the Milky Way must contain far more mass than visible stars and gas could provide. When researchers recalculated the galaxy's mass using these orbits, the result was staggering. The Milky Way's total mass had to be several trillion times the mass of the Sun. This was not a small correction. It was a complete reclassification. The Milky Way was no longer a modest spiral galaxy. It was a heavyweight. Beyond the Magellanic Clouds lies an entire population of dwarf galaxies, dozens confirmed, and many more suspected. These dwarfs orbit at a wide range of distances and angles, forming a loose swarm around the Milky Way. Each one acts as a test particle, its motion shaped by the galaxy's gravitational field. When astronomers measured these motions, a consistent pattern emerged. The dwarfs were moving faster than expected and orbiting farther out than old models allowed. Some circled at distances approaching 200,000 light-years, yet remained bound. The only way to explain this behavior was to dramatically increase the Milky Way's mass. These dwarf galaxies provided something earlier methods lacked: direct measurements of gravity at extreme distances. Counting stars or mapping light could miss faint components. Orbital dynamics could not. Gravity does not care whether matter is bright or dark. If it pulls, it counts. When scientists combined the data from satellite galaxies with stellar streams and dark matter models, the conclusion solidified. The Milky Way contains roughly 4 trillion solar masses, possibly more. Most of that mass is dark matter, spread through an enormous halo. This placed the Milky Way on nearly equal footing with Andromeda, long considered the dominant galaxy in the local group. The implications were immediate. A galaxy with that much mass commands a far larger region of space. Its gravitational reach extends farther. It can capture more satellites, strip stars more efficiently, and dominate its cosmic neighborhood. The Milky Way is not a passive member of the local group. It is an active gravitational power. The satellite galaxies are not merely companions. They are evidence of dominance. Many are slowly being torn apart, their stars stretched into streams that will eventually merge with the halo. Others are on long, slow death spirals, destined to be absorbed over billions of years. This behavior only makes sense if the Milky Way is both massive and extended. The revised mass estimates also explain why so many satellites remain bound instead of drifting away. The galaxy's gravitational well is deep, far deeper than previously imagined. When viewed through the lens of its satellites, the Milky Way transforms from a familiar spiral into a massive gravitational system, capable of shaping the motion of dozens of galaxies across hundreds of thousands of light years. The satellites do not lie. Their orbits are written in gravity, and gravity makes one thing clear. The Milky Way is not a lightweight galaxy that happens to host us. It is a giant, quietly ruling a vast region of space we are only beginning to understand. Once the Milky Way's mass and reach were recalculated, another problem surfaced immediately. The human mind is not equipped to understand what those numbers actually mean. 200,000 light-years sounds like an abstract correction, a larger figure replacing a smaller one. But at galactic scales, doubling a number does not simply mean twice as much. It breaks intuition completely. A light-year is already beyond everyday comprehension. Light travels nearly 300,000 kilometers every second. Yet even at that unimaginable speed, it takes an entire year to cross a single light year. Now multiply that distance by 200,000. You're no longer dealing with space as humans experience it, but with time itself. If you could travel at the speed of light, the absolute speed limit of the universe, it would still take 200,000 years to cross the Milky Way from edge to edge. When light leaves one side of the galaxy, it arrives at the other side long after civilizations rise, fall, and disappear. That is the scale we are talking about. And distance alone does not capture the shock. Volume makes it worse. Galaxies are three-dimensional structures. When you double the diameter of a galaxy, you do not double its size. You increase its volume by a factor of 8. That means 8 times more space, 8 times more room for stars, planets, and everything else. The old picture of the Milky Way already contained hundreds of billions of stars. The revised picture forces astronomers to rethink that number entirely. If the galaxy is twice as wide, its total volume expands dramatically, even if the outer regions are sparse. Sparse does not mean empty. When you integrate that extra volume, the numbers climb fast. Estimates that once hovered around 200 billion stars now push toward 400 billion, possibly more. Most of these additional stars are not bright suns like our own. They are dim red dwarfs, faint and long-lived, scattered throughout the outer regions and halo. Individually, they are easy to miss. Collectively, they dominate the population. This explains why earlier surveys failed to count them. They hide in darkness, contributing almost no light while quietly adding enormous numbers. The realization forces a recalibration of everything tied to star counts. More stars mean more planetary systems. More planets mean more opportunities for complex chemistry, oceans, and potentially life. Even conservative estimates multiply quickly when the base number doubles. The galaxy did not merely grow larger on paper. It became more crowded, more complex, and more statistically rich. This scale shock is not just mathematical, it is existential. Humans evolved to understand distances measured in steps, kilometers, maybe planetary orbits. Our brains did not evolve to grasp volumes spanning hundreds of thousands of light years. Yet this vast structure is our home. We orbit quietly within one small spiral arm, embedded in a galaxy so large that light itself struggles to cross it within the span of human history. The correction from 100,000 to 200,000 light-years is not a footnote. It is a reminder that even our most familiar cosmic landmarks exist on scales that overwhelm human intuition, and that the universe is far larger, denser, and more populated than it ever appears from our small corner within it. Once the scale of the Milky Way expanded, the consequences rippled far beyond astronomy and into one of humanity's oldest questions: are we alone? Size matters because probability cares about numbers, and the galaxy just provided many more of them. When astronomers say the Milky Way may contain 400 billion stars instead of 200 billion, that is not a cosmetic change. It is a fundamental shift in the statistical landscape of life. Every star is a potential host. Every planetary system is a laboratory. Doubling the number of stars doubles the number of opportunities for planets, chemistry, and eventually biology. The galaxy did not simply grow larger, it became far more fertile in possibility. To understand why this matters, start with something already established. Planets are common. This is no longer speculation. Observations from space telescopes have shown that most stars host planets, often multiple ones. Planetary systems are not rare accidents. They are the default outcome of star formation. Even conservative estimates suggest that at least half of all stars have planets. Apply that fraction to 400 billion stars, and you're already looking at hundreds of billions of planetary systems. That alone dwarfs every previous assumption humans made about the cosmic environment. But planets are not equal. The real interest lies in habitable zones, the regions around stars where temperatures allow liquid water to exist on a planet's surface. Liquid water is not a guarantee of life, but on Earth it was essential. Habitable zones vary widely depending on the star. Small red dwarfs have narrow zones close in. Sun-like stars have wider zones farther out. Giant stars push their zones even farther. Across 400 billion stars, habitable zones are everywhere. If even a modest fraction of planetary systems place a planet in that zone, the number of potentially habitable worlds explodes. Earlier estimates already suggested billions. Doubling the galaxy's size pushes those estimates even higher. What once sounded optimistic now becomes conservative. This is where the numbers become uncomfortable. If billions of planets have conditions suitable for life, then life itself must be examined statistically, not emotionally. We have one confirmed data point: Earth. Life appeared here relatively early once conditions stabilized. Within a few 100 million years of oceans forming, biology was already present. That speed suggests that life, at least simple life, might not be extraordinarily rare given the right conditions. But one example is not a trend. Scientists remain cautious. Life might be common, or it might be an extraordinary fluke. The uncertainty spans orders of magnitude. This is where the Drake equation enters the conversation. The Drake equation is not a formula that produces a single answer. It is a framework for thinking about probability. It breaks the problem into steps. How many stars exist? How many have planets? How many of those planets are habitable? How many develop life? How many develop intelligence? How many produce detectable technology? And how long such civilizations last? Every term in that equation carries uncertainty. But the first term, the number of stars, just doubled. That change propagates through the entire equation. Even if all other factors remain unchanged, the expected number of technological civilizations increases. Probability does not care about pessimism. It multiplies whatever numbers you give it. Suppose life is rare, extremely rare. 1 in a million habitable planets. In a smaller galaxy, that might yield a handful of living worlds. In a galaxy twice as large, it yields twice as many. Suppose intelligence is rarer still. 1 in a million living worlds. The number shrinks dramatically, but it does not go to zero. With enough planets, even unlikely outcomes eventually occur. The expanded Milky Way makes that statistical inevitability harder to ignore. This reframes the famous Fermi paradox. The paradox is often summarized simply: if the galaxy is so vast and old, and if life and intelligence are not extremely rare, then where is everybody? Why do we see no clear evidence of extraterrestrial civilizations? No signals, no probes, no obvious engineering on a galactic scale. The paradox assumes a certain size and density for the galaxy. But if the Milky Way is larger than assumed, the paradox changes shape. Distances grow. Search volumes expand. Signals weaken faster. Civilizations become more isolated by sheer scale. A radio signal traveling at the speed of light takes tens of thousands of years to cross the galaxy. If a civilization broadcasts for a short technological window, its signal might never intersect ours. If civilizations are sparse and far apart, silence becomes less surprising. A larger galaxy gives loneliness more room to exist. At the same time, the paradox becomes sharper in another way. More stars also mean more chances for civilizations to arise somewhere at some time. The galaxy is over 13 billion years old. Even if civilizations are rare and short-lived, the sheer number of opportunities should produce overlap. The absence of evidence remains unsettling. But now it must be interpreted in the context of a galaxy whose scale we underestimated. The haystack we are searching for needles in just became vastly larger. This directly affects the search for extraterrestrial intelligence. SETI efforts scanned small portions of the sky, limited frequency ranges, limited time windows. Even optimistic programs have examined only a tiny fraction of the possible search space. Doubling the number of stars doubles the number of potential transmitters, but it also doubles the search volume. The task becomes harder and more urgent at the same time. A larger galaxy means we must be more strategic, not more hopeful by default. It also reshapes expectations about detectability. Civilizations might exist, but remain undetectable due to distance, technological choices, or sheer timing. A signal sent 100,000 years ago from the far side of the galaxy may have already passed Earth before humans had radio technology. Another might not arrive for tens of thousands of years yet. The galaxy's size stretches communication across epochs, not just space. That temporal separation alone could explain the silence. The expanded star count also affects the likelihood of non-technological life. Simple life may be common even if intelligence is rare. Microbial ecosystems could exist on countless worlds, hidden beneath oceans or ice, never broadcasting anything detectable. The Milky Way could be teeming with life and still appear silent. This possibility becomes more plausible as the number of habitable environments grows. The galaxy does not need to host galactic empires to be biologically rich. It only needs chemistry, time, and enough planets. From this perspective, the question shifts. Instead of asking why we have not been contacted, we ask how often contact is realistically possible. Interstellar distances, even within a single galaxy, impose severe constraints. Travel is slow. Communication is delayed. Expansion requires enormous energy and long-term stability. A larger galaxy magnifies these challenges. It favors isolation over interaction, yet it also strengthens the case that life itself is widespread. The numbers tilt the balance toward biology, even if they leave technology uncertain. This dual outcome is what makes the revision so powerful. It simultaneously increases the probability that life exists elsewhere and decreases the expectation that we should have already encountered it. Both conclusions follow logically from scale. The galaxy's expanded size also changes how scientists prioritize future searches. Instead of assuming nearby stars are representative, researchers must consider that the outer regions of the galaxy host vast numbers of stars that were previously ignored. Many of these stars are older, metal-poor, and different from those in the inner disk. Their planetary systems may follow different evolutionary paths. Life in those regions, if it exists, may not resemble life near the galactic centers. Diversity increases with size. The Milky Way becomes not just bigger, but more varied. This diversity complicates predictions. It also enriches them. A galaxy with 400 billion stars is not a single experiment repeated many times. It is billions of experiments running under different conditions. Some regions are dense and violent, bombarded by radiation. Others are quiet and stable for billions of years. Some stars are short-lived and bright. Others burn slowly for trillions of years. Each environment shapes life differently. The search for extraterrestrial intelligence must account for this complexity. A one-size-fits-all expectation no longer makes sense. The expanded galaxy also affects how we think about humanity's future. If intelligent life is rare but not unique, then civilizations may be separated by vast distances and times. Contact might be possible only through artifacts, not conversations. Ancient signals, long-dead transmitters. A larger Milky Way increases the likelihood that such relics exist somewhere, even if they are difficult to detect. It also raises the possibility that civilizations rise and fall without ever knowing of each other's existence. The galaxy becomes a stage for countless isolated stories rather than a connected network. This perspective softens the emotional weight of the Fermi paradox. Silence does not necessarily imply emptiness. It may simply reflect scale. From inside a structure 200,000 light-years wide, silence is the default condition. Against that backdrop, even a few signals would be extraordinary. SETI's task becomes one of patience and precision rather than expectation. Doubling the galaxy's size does not guarantee discovery. It justifies continued searching. It makes the effort rational rather than romantic. The revised star count also influences estimates of technological longevity. If civilizations are rare and fragile, most may extinguish themselves quickly. In a larger galaxy, their brief flashes are harder to overlap. The silence could be a graveyard effect rather than evidence of absence. The expanded Milky Way allows many civilizations to exist without ever intersecting in time or space. This does not solve the paradox, but it reframes it in a way that aligns better with known physics and biology. In the end, the galaxy's revised size does not answer the question of life. It amplifies it. It stretches probability across a larger canvas. It increases both hope and humility. Humans are one species orbiting one star among hundreds of billions. inside a galaxy whose true scale we only recently began to understand. That realization alone is transformative. Whether or not we ever detect another civilization, the Milky Way's expansion forces a change in perspective. Life is no longer a question confined to a modest spiral with neat boundaries. It is a question embedded in a vast, sprawling, ancient system where distance, time, and chance dominate. The galaxy just got bigger. The silence became more understandable, and the possibility that life exists elsewhere became harder to dismiss, not because of optimism, but because the numbers now demand it. As the implications for life settled in, astronomers were forced to confront another consequence of a larger Milky Way. Its internal structure was far messier than the clean spiral diagrams suggested. The familiar image of a graceful galaxy with a fixed number of well-defined arms began to unravel under closer scrutiny. For decades, textbooks confidently showed 4 spiral arms, neatly labeled and symmetrically arranged around the galactic centers. That picture relied heavily on observations of bright gas clouds and young stars, the easiest features to detect. But once surveys expanded outward and inward, cutting through dust and mapping stellar motions rather than light alone, the structure became far more complicated. Some arms appeared to split, others faded and reappeared. New features emerged where none were expected. The Milky Way, it turned out, does not follow a simple blueprint. Part of the problem lies in perspective. From inside the disk, spiral arms overlap along our line of sight, making it difficult to tell where one ends and another begins. Dust obscures large portions of the galaxy, especially toward the center, hiding entire regions from optical view. Early astronomers traced arms by following bright star-forming regions, assuming they marked continuous structures. In reality, these regions are patchy and transient. When infrared and radio observations peeled back the dust, they revealed additional arms, spurs, and branches that did not fit the old model. The local arm, once thought to be a minor spur, may be a major structure in its own right, extending farther than expected. The outer arm, long dismissed as scattered debris, shows signs of organization deep into the galaxy's outskirts. The confusion deepens when theory enters the picture. Spiral arms are not solid structures made of the same stars over time. They are density waves, regions where stars and gas bunch up temporarily as they orbit the galactic center. Stars move through these waves much like cars moving through a traffic jam. The jam persists, but the individual cars do not stay in it. This explains why spiral arms can last for billions of years without winding themselves into oblivion. Yet observations challenge even this explanation. Some arms contain too many young stars to be explained by a simple wave. Others appear too massive or too extended. In a galaxy now known to be much larger, with more mass and a more complex gravitational field, these discrepancies become harder to ignore. The expanded dark matter halo likely plays a role, shaping spiral patterns in ways older models never accounted for. Gaia's precise mapping of stellar motions exposed this complexity in unprecedented detail. Instead of smooth, continuous arms, the data revealed substructure everywhere. Branches, gaps, ripples, and asymmetries appeared throughout the disk. The Milky Way began to look less like a grand design spiral and more like a chaotic, evolving system shaped by past mergers and ongoing interactions. Some astronomers now argue that the galaxy may not have a fixed number of arms at all. It may be a flocculent spiral with loosely organized features that change over time. In a galaxy twice as large and far more massive than once believed, this chaos makes sense. More mass means stronger gravitational interactions, more perturbations, and a longer history of collisions. The Milky Way's structure is not frozen. It is dynamic, constantly reshaped by forces acting across hundreds of thousands of light-years. The revised size does not merely stretch the galaxy outward. It reshapes our understanding of its internal order, revealing a system far more complex, turbulent, and alive than the tidy spiral we once imagined. This growing awareness of complexity leads directly to another uncomfortable realization. Defining where the Milky Way ends is not just difficult, it may be fundamentally impossible. Once astronomers accepted that spiral arms are fluid, transient features, and that dark matter dominates the galaxy's structure, the idea of a clean boundary began to dissolve. The Milky Way does not have an edge in the way a continent has a coastline. There is no line you can draw and confidently say, "Beyond this point, the galaxy is over." Star density simply decreases. Gas becomes thinner. Dark matter fades gradually into the cosmic background. Every attempt to define an edge depends on an arbitrary choice. If you define the galaxy by visible stars, you get one size. If you define it by gravitational binding, you get a much larger one. If you define it by dark matter influence, the size grows larger still. This is not a failure of measurement. It is a reflection of how nature works. The universe does not respect human categories. From this perspective, the Milky Way is better understood as a region of influence rather than an object. Near the center, gravity dominates absolutely. Stars are densely packed, orbits are tight, interactions are frequent. Farther out, the grip weakens but does not disappear. Stars orbit more slowly, paths become elongated, and some objects hover near escape velocity, barely bound, undecided between staying and leaving. These marginal stars are especially revealing. They occupy the gray zone between galaxy and intergalactic space, showing that the transition is smooth, not abrupt. Some will eventually escape. Others will remain bound for billions of years. Their existence makes any sharp definition of inside versus outside feel artificial. The same applies to gas. Powerful stellar winds and supernova explosions push material far into the halo. Some of this gas will cool and fall back, feeding future generations of stars. Some will drift away permanently. At any given moment, large amounts of matter exist in transit, neither fully part of the disk nor fully detached. Is that material part of the Milky Way? The answer depends entirely on perspective. Even satellite galaxies complicate the picture. They orbit within the Milky Way's gravitational field, clearly influenced by it, yet they are still considered separate entities until they merge. Over time, many will be torn apart and absorbed, their stars becoming indistinguishable from the rest of the halo. At that point, their former identity disappears. Looking backward, we call them galaxies. Looking forward, they are simply future components of the Milky Way. This blurring of boundaries is not an inconvenience to be resolved. It is a clue. It tells us that the Milky Way is not a static structure with a fixed shape and size. It is an evolving system, constantly exchanging matter with its surroundings, growing through mergers, shedding material through winds, and reshaping itself under the influence of gravity and time. The revised size estimate does not mark the final answer. It marks a shift in thinking. Instead of asking for a precise edge, astronomers now ask better questions. How far does gravity dominate? How does matter move at the outskirts? And how does the galaxy interact with its environment? Those questions acknowledge what the data has been quietly telling us all along. The Milky Way is not a neatly bounded spiral floating in empty space. It is a vast, diffuse, dynamic region of influence, and we live deep inside it, still learning where home truly fades into the wider universe. Once boundaries lose their meaning, the focus shifts from edges to motion. What matters is not where the Milky Way supposedly stops, but how things move within and around it. And this is where the revised size creates another shock. Stars at the outskirts of the galaxy behave in ways that should not be possible under older models. In a simple gravitational system, objects farther from the center should move more slowly. This is how our solar system works. Mercury orbits the Sun quickly. Neptune crawls along at a distant pace. Gravity weakens with distance, and motion reflects that weakening. For decades, astronomers expected galaxies to follow the same rule. They did not. Even before the Milky Way's size was revised, stars near the edge were already moving too fast. That discrepancy is what led to the idea of dark matter in the first place. But expanding the galaxy made the problem sharper, not smaller. With stars and stellar streams now known to orbit much farther out, their speeds become even harder to explain. Some stars in the outer halo move at velocities just below escape speed. They are barely bound, skating along the edge of freedom. A difference of a few kilometers per second would send them drifting into intergalactic space forever, yet they remain. This behavior reveals how deep the Milky Way's gravitational well truly is. A galaxy that can hold on to stars at such distances must be enormously massive. It also suggests that the outer halo is a dynamic environment, constantly reshaped by past mergers and ongoing interactions. Many of these fast-moving stars likely came from devoured galaxies. When smaller systems were torn apart, their stars were flung into wide, elongated orbits. Over billions of years, these stars mixed into the halo, forming a population that carries the kinematic memory of ancient collisions. The Milky Way's outskirts are not quiet or empty. They are crowded with relics of violence, each star tracing a history written in motion. The revised scale also forces astronomers to reconsider escape itself. If the galaxy is larger and more massive, escape becomes harder. Objects once thought to be unbound may actually remain trapped for cosmic timescales. Conversely, stars we assumed were safely orbiting may eventually drift away as gravitational tides from neighboring galaxies pull at the halo. The Milky Way is not isolated. Its dark matter halo overlaps, or will soon overlap, with that of Andromeda. Even now, the outermost regions feel competing gravitational influences. This interaction further blurs the distinction between belonging and leaving. At the largest scales, galaxies do not exist alone. They exist in fields of influence that overlap, merge, and evolve. Understanding motion at the outskirts of the Milky Way is therefore not just about our galaxy. It is about how galaxies behave in groups, how they exchange matter, and how structure emerges in the universe. The expanded size of the Milky Way turns its halo into a laboratory for testing gravity, dark matter, and galaxy evolution under extreme conditions. Every fast-moving star, every distorted stream, every marginally bound object adds another data point. Together, they show that the galaxy's true complexity lies not in its bright center, but in its faint, extended outskirts, where gravity whispers rather than shouts, and where the Milky Way quietly reveals just how massive and far-reaching it really is. As the implications for life and probability expanded outward, attention returned inward, toward the structure of the galaxy itself. If the Milky Way was larger, heavier, and more dynamic than we believed, then its internal architecture could no longer be assumed to be simple. For much of the 20th century, the galaxy was presented as a classic spiral, elegant and orderly, with a fixed number of arms curling gracefully around a bright central bulge. That image was comforting. It suggested symmetry, predictability, and stability. But as the data improved, that picture began to fracture. The Milky Way does not behave like a clean textbook spiral. It behaves like a system in flux. The first cracks appeared when astronomers tried to agree on something seemingly basic. How many spiral arms does our galaxy actually have? Depending on the method used, the answer changed. Optical surveys emphasized regions of active star formation and suggested 4 major arms. Radio observations of hydrogen gas hinted at additional structures. Infrared surveys, able to peer through dust, revealed arms that optical telescopes had missed entirely. What once looked like a tidy pattern now resembled overlapping sketches drawn at different times, none fully consistent with the others. The problem was not sloppy science, it was perspective. From inside the disk, spiral arms overlap along our line of sight. Dust blocks some regions while revealing others. Bright young stars highlight only certain segments. Older stars tell a different story. Every wavelength traces a different component of the galaxy, and none of them alone provides a complete map. For decades, astronomers stitched these partial views together, assuming the underlying structure was simple. Gaia changed that assumption. By measuring the positions and motions of more than 1 billion stars, Gaia transformed the Milky Way from a flat picture into a dynamic system. Instead of tracing arms by brightness, astronomers could now trace them by motion. Stars that move together likely share a common structure. When researchers applied this approach, the spiral pattern became far more complicated than expected. Arms split into branches. Branches reconnected. Spurs extended outward at odd angles. Some features appeared coherent over large distances, while others dissolved quickly. The galaxy's spiral structure was not a static scaffold. It was a living pattern, constantly reshaped by gravity, motion, and time. One of the most striking revelations concerned our own neighborhood. The solar system resides in what was long called a minor spur, the Orion Arm, thought to be a small bridge between larger structures. Gaia data suggested something more significant. The local arm may be a major feature in its own right, extending farther and containing more stars than previously believed. This reclassification alone altered maps that had been reproduced for generations. But it was only the beginning. The outer regions of the galaxy revealed even greater surprises. Areas once dismissed as sparse or chaotic showed signs of organized structure. The outer arm, near the edge of the visible disk, appeared more continuous and massive than expected. In a galaxy now known to be larger, this made sense. More mass and more space allow spiral features to persist farther out. Yet this raised a deeper question. What are spiral arms, really? For a long time, they were imagined as material structures, collections of stars moving together through space. That idea quickly ran into a problem. Stars closer to the galactic center orbit faster than stars farther out. If spiral arms were fixed groups of stars, differential rotation would wind them tighter and tighter until they vanished. This should happen in a few 100 million years, far shorter than the age of the galaxy. Yet spiral arms persist. To resolve this, astronomers proposed density wave theory. According to this idea, spiral arms are not fixed collections of stars, but waves of higher density that move through the disk. Stars enter the wave, slow down, bunch up, and then leave, much like cars entering and exiting a traffic jam. The jam persists even though individual cars do not. This theory explained why arms could last for billions of years. It also explained why star formation is concentrated in arms. Gas clouds compress as they pass through the density wave, triggering new stars. Density wave theory worked well on paper, but reality proved more complicated. Observations showed arms that did not behave like simple waves. Some arms appeared too massive, too sharply defined, or too irregular. Others showed signs of being pulled or distorted, as if external forces were at work. In a galaxy with a massive dark matter halo and a long history of mergers, such forces are unavoidable. Past collisions leave scars. Accreted galaxies tug on the disk. Satellite galaxies perturb stellar orbits. Even the dark matter halo itself, if lumpy rather than smooth, can influence spiral patterns. Gaia data revealed ripples in the disk, vertical waves, and asymmetries that density wave theory alone could not easily explain. Some of these features appeared to be echoes of past encounters. When a dwarf galaxy passes through the disk, it can send waves of motion rippling outward, much like a stone dropped into a pond. These ripples persist for hundreds of millions of years. They distort spiral arms, create gaps, and generate new substructures. In a larger galaxy with more satellites and a deeper gravitational well, such disturbances are more frequent and longer lasting. The Milky Way's spiral pattern is therefore not just a product of internal dynamics, but a record of its interaction history. The idea of a single clean spiral design becomes untenable. Instead, the galaxy resembles a tangled system of overlapping patterns, some long-lived, others transient, all evolving together. This has led some astronomers to argue that the Milky Way may be a flocculent spiral, a galaxy with patchy, ill-defined arms rather than a grand, symmetrical design. In such galaxies, arms form, dissolve, and reform over time, driven by local instabilities rather than a single global wave. The distinction matters because it changes how we think about galactic evolution. A grand design spiral suggests stability and order. A flocculent spiral suggests chaos and continual change. The Milky Way may sit somewhere between these extremes, its structure shaped by both long-lived density patterns and short-lived perturbations. The expanded size and mass of the galaxy tip the balance toward complexity. More mass means stronger self-gravity. Stronger gravity amplifies instabilities. A larger disk is more susceptible to bending, warping, and fragmentation. Indeed, the Milky Way's disk is warped, twisting upward on one side and downward on the other. This warp extends far into the outer regions and is likely influenced by interactions with satellite galaxies and the dark matter halo. Such features are not anomalies. They are natural outcomes of a massive extended system. Even the central bar of the Milky Way adds to the chaos. The galaxy hosts a bar-shaped structure of stars at its center, rotating as a rigid body. This bar interacts with spiral arms, exchanging angular momentum and reshaping orbits. In some models, spiral arms are driven or reinforced by the bar. In others, they arise independently. The interaction between bar and arms creates resonances, regions where stellar orbits align in complex ways. These resonances can enhance or suppress star formation, alter arm shapes, and create rings or gaps. In a larger galaxy, these effects extend over greater distances and involve more stars, increasing complexity further. The clean diagrams of the past cannot capture this behavior. They freeze a dynamic system into a static image. Gaia's data, by contrast, reveals motion, evolution, and imperfection. It shows that the Milky Way is not a finished object, but an ongoing process. Arms are not permanent fixtures. They are patterns emerging from the collective motion of billions of stars, shaped by gravity, history, and chance. The revised size of the galaxy magnifies this truth. With more stars and a larger disk, there are more opportunities for patterns to form and dissolve. The galaxy's structure becomes richer and less predictable. This has implications beyond aesthetics. Spiral structure influences star formation, chemical evolution, and the distribution of planets. Regions near arms experience bursts of star formation. Regions between arms are quieter. As arms move and change, so do the environments in which stars and planets form. The solar system's own history may have been influenced by past passages through spiral arms, exposing Earth to varying radiation environments and supernova rates. In a galaxy with chaotic spiral structure, such passages may be irregular and unpredictable. The expanded Milky Way therefore affects not only where stars are, but how they live and evolve. The growing picture is one of organized chaos. Gravity imposes structure, but that structure is constantly perturbed. Dark matter provides a deep gravitational backdrop, but it does not enforce symmetry. Past mergers inject disorder. Bars and arms exchange energy. Satellite galaxies stir the disk. Over billions of years, the galaxy becomes a layered record of these processes. The tidy spiral image survives only as a rough approximation, useful for teaching but misleading in detail. The Milky Way is not a simple spiral etched into space. It is a turbulent, evolving system whose structure reflects its mass, size, and history. Accepting this messiness is part of accepting the galaxy's true scale. A small, light galaxy might maintain a clean pattern. A massive, extended one cannot. The chaos is not a flaw in our understanding. It is the reality that better data finally allows us to see. This recognition of chaos also forces a reassessment of how astronomers model the Milky Way at all. For decades, simulations relied on simplifying assumptions: smooth disks, symmetric halos, steady spiral patterns. These models were necessary because data was limited. You cannot model complexity you cannot see. But Gaia, combined with radio and infrared surveys, exposed the cost of those simplifications. When real stellar motions were plotted, they refused to line up with idealized expectations. Stars that should have shared similar orbits diverged. Groups that should have dispersed remained coherent. Velocity patterns appeared tilted, warped, and offset. The galaxy behaved less like a polished mechanism and more like a crowded system shaped by continual disturbance. This matters because structure is memory. Every irregularity encodes a past event. A ripple in stellar motion can trace back to a satellite galaxy that passed through the disk hundreds of millions of years ago. A warped outer arm may point to long-term gravitational tugging from the dark matter halo or from the Magellanic Clouds. Vertical oscillations in the disk suggest the galaxy is still ringing from ancient impacts, like a bell struck long ago that has not yet gone quiet. In a Milky Way twice as large as once believed, these echoes have more room to persist and propagate. The galaxy does not relax quickly. Its immense mass and scale slow down the settling process. Disturbances linger. This helps explain why the Milky Way looks dynamically young despite its age. At over 13 billion years old, it should be well settled. Instead, it appears restless. The expanded size resolves part of this contradiction. Larger systems take longer to equilibrate. The galaxy's chaotic structure is not a sign of youth, but a consequence of scale. Another implication concerns predictability. In a clean spiral model, future structure can be extrapolated with confidence. In a messy, perturbed system, long-term predictions become probabilistic rather than deterministic. Spiral arms may strengthen, weaken, shift, or dissolve. Star formation regions migrate. The bar may grow or slow. The disk warp may increase or dampen. These changes occur over hundreds of millions of years, invisible on human timescales, but critical for understanding galactic evolution. A larger Milky Way amplifies this uncertainty. More mass means stronger non-linear effects. Small perturbations can have large consequences over time. From this perspective, the Milky Way resembles a weather system more than a machine. Large-scale patterns exist, but local conditions matter. Order and disorder coexist. This also reframes the role of our solar system. The Sun's orbit is not a perfect circle in a static disk. It is a path through a shifting gravitational landscape. Over billions of years, the solar system has likely migrated radially, moved up and down relative to the disk, and experienced varying environments as spiral structures evolved around it. In a galaxy now known to be larger and more complex, such migration becomes more likely. The Sun's current position may not reflect its birthplace. The Milky Way is not just where we are. It is something we have been moving through since the beginning. Ultimately, the lesson of galactic structure is the same lesson revealed by size, mass, and dark matter. The Milky Way resists simplicity. Every time observations improve, the picture becomes richer, messier, and more demanding. Spiral arms are not clean lines. They are patterns emerging from motion. The galaxy is not a static object. It is a dynamic system shaped by gravity, history, and chance on scales that overwhelm intuition. Accepting this complexity is not a failure of understanding. It is progress. The Milky Way is finally being seen not as a diagram, but as what it truly is: a vast, evolving, chaotic structure, and we are embedded deep within it, trying to map a storm from the inside. As the Milky Way's chaotic structure came into focus, one explanation began to unify many of its mysteries. The galaxy did not grow quietly. It grew by consuming others. The messiness of its spiral arms, the ripples in its disk, the strange motions of stars in the halo, and the sheer scale of its mass all point to a violent history of mergers and destruction. The Milky Way is not a pristine object that formed once and settled into place. It is the product of repeated acts of galactic cannibalism. Over billions of years, it has pulled in, torn apart, and absorbed smaller galaxies, adding their stars, gas, and dark matter to its own body. Growth at galactic scales is rarely gentle. In the early universe, small galaxies were far more common than large ones. Gravity drew them together, and larger systems grew by swallowing smaller neighbors. The Milky Way was no exception. In fact, its current size almost guarantees a long history of mergers. A galaxy this massive does not arise in isolation. Each collision left traces, and for a long time, those traces were invisible. Stars from devoured galaxies mixed into the Milky Way's halo, losing their original identity. To earlier astronomers, the halo looked like a smooth, ancient population, a quiet, spherical cloud surrounding the disk. But Gaia shattered that illusion. When stellar motions and chemical compositions were examined in detail, the halo revealed itself as a mosaic of immigrants. Many of its stars do not share a common origin. They move differently. They carry different chemical signatures. They remember different birthplaces. One of the most dramatic revelations was the discovery of Gaia Enceladus. This was not a minor accretion event. It was a major collision between the early Milky Way and a galaxy nearly a quarter of its size. The evidence lay hidden in plain sight. A large population of halo stars showed highly elongated orbits, plunging toward the galactic center and then flinging far outward. Their motions were unlike those of stars formed in the Milky Way's disk. Chemically, they were distinct as well, poorer in heavy elements, consistent with a separate evolutionary history. When astronomers reconstructed their trajectories, the picture became clear. Around 10 billion years ago, a substantial galaxy fell into the Milky Way and was torn apart. Its core was destroyed. Its stars were scattered. Its dark matter merged into the Milky Way's halo. The event was so significant that it likely reshaped the galaxy's entire structure. Before the collision, the Milky Way may have been a smaller, thinner disk. Afterward, it became thicker, more turbulent, and more massive. Gaia Enceladus did not just add stars, it changed the galaxy's destiny. This realization reframed the halo entirely. The halo is not simply an ancient remnant from the Milky Way's formation. It is a graveyard of galaxies, each layer representing a different merger event. Some contributions were massive, like Gaia Enceladus. Others were smaller, quieter, but still detectable. As Gaia's data was mined more deeply, additional structures emerged. One of the most enigmatic is a proposed merger nicknamed Kraken. Unlike Gaia Enceladus, Kraken is harder to pin down. Its stars are more mixed, their signatures blurred by time. But statistical analyses suggest that another large galaxy may have merged with the Milky Way even earlier, contributing significantly to the halo's mass. If true, Kraken would represent a formative event, shaping the Milky Way before its disk fully settled. These ancient mergers occurred when the universe was young, when galaxies were gas-rich and chaotic. Their impacts would have stirred the Milky Way violently, triggering bursts of star formation, heating the disk, and redistributing angular momentum. The result would be a galaxy already complex long before later smaller mergers took place. Galactic cannibalism did not end in the distant past. It is still happening. The Sagittarius dwarf galaxy is being torn apart right now. Discovered only in the late 20th century, Sagittarius orbits the Milky Way on a polar path, plunging through the disk again and again. Each passage strips stars from its body, stretching them into a long stellar stream that wraps around the galaxy. Eventually, Sagittarius will disappear entirely, its stars fully absorbed into the halo and disk. This is not a rare event. It is simply the most visible current example. Dozens of smaller dwarf galaxies orbit the Milky Way, and many will share the same fate over the next few billion years. Each merger adds mass, stirs structure, and leaves behind streams, ripples, and asymmetries. In a galaxy as large as the Milky Way, these events accumulate. They overlap. Their signatures blur but never fully vanish. This helps explain why the halo is so extended and why it reaches far beyond the visible disk. Many of its stars did not form in place. They arrived from elsewhere, flung into wide orbits by the violence of accretion. The halo is not just old, it is foreign. And that realization carries an unsettling implication. A significant fraction of the stars surrounding us are not native to the Milky Way at all. They are immigrants from destroyed galaxies. Their atoms were forged in different environments, under different histories, before becoming part of our galaxy. Some of those atoms eventually found their way into the disk, into later generations of stars, into planets. The Sun itself likely contains material contributed by ancient mergers. The iron in your blood, the calcium in your bones. The oxygen you breathe may include atoms that once belonged to entirely different galaxies. In a literal sense, we are made of alien matter. This is not metaphorical. It is chemical fact. Galactic cannibalism is how heavy elements spread. Smaller galaxies form stars, enrich their gas, and then are consumed, donating their processed material to larger systems. Without this recycling, galaxies like the Milky Way would be poorer in elements essential for rocky planets and life. Cannibalism, brutal as it sounds, is part of cosmic ecology. It is how complexity grows. The Milky Way's current richness is the result of countless destructions. Its beauty is built on loss. This perspective also deepens the connection between the galaxy's size and its history. A larger Milky Way implies more mergers. More mergers imply more chaos, thicker disks, larger halos, and more substructure. Everything fits together. The revised size is not an isolated correction. It is the natural outcome of a long, violent growth process. To understand the Milky Way is to accept that it is a composite object, stitched together from many ancestors. The neat idea of a single continuous formation gives way to a story of accumulation. We live inside a galaxy assembled from ruins. The consequences of this cannibalistic history reach far beyond the halo. They penetrate the disk itself, altering the Milky Way's shape, thickness, and long-term stability. When a galaxy consumes another, the impact is not limited to the outskirts. Gravitational shocks propagate inward, heating stellar orbits and puffing up what might otherwise be a thin, orderly disk. This helps explain why the Milky Way has both a thin disk and a thick disk, two overlapping stellar populations with very different properties. The thin disk contains younger stars, including the Sun, moving in relatively calm, circular orbits. The thick disk, by contrast, is older, kinematically hotter, and more vertically extended. For years, astronomers debated how this thick disk formed. Was it an early phase of star formation? Was it the result of internal dynamics? The merger history provides a compelling answer. Major collisions like Gaia and Enceladus would have violently disturbed the early disk, scattering stars into higher orbits and creating a thickened component. Later, as the galaxy settled, a thinner disk could reform from cooled gas. The Milky Way, in this view, rebuilt itself after trauma. This cycle of disruption and regrowth is a hallmark of large galaxies. Cannibalism does not simply add mass, it resets structure. Each major merger rearranges stellar orbits, redistributes gas, and triggers new waves of star formation. Some stars are flung outward into the halo. Others sink inward. Gas clouds collide, compress, and ignite. Over time, these events layer the galaxy with populations of different ages, motions, and chemical compositions. The Milky Way's disk is therefore not a single coherent population. It is a palimpsest, written over many times by successive mergers. Chemical evidence reinforces this picture. Stars carry the fingerprints of their birth environments in their elemental abundances. By comparing ratios of elements like iron, magnesium, and oxygen, astronomers can identify stars that formed in different galaxies. Gaia-enabled surveys revealed that many halo stars share chemical patterns distinct from disk stars. Even within the disk, some stars show signatures of extragalactic origin. These stars did not form in the Milky Way's original gas cloud. They were born elsewhere and later incorporated. The galaxy's stellar population is a blended archive of multiple evolutionary histories. This blending complicates any attempt to define a typical Milky Way star. There is no single origin story, Cannibalism also helps explain the Milky Way's unusually massive dark matter halo. When galaxies merge, their dark matter halos merge as well, overlapping and combining into a larger gravitational envelope. Over billions of years, repeated accretion events inflate the halo, extending its reach far beyond the visible disk. This is why the Milky Way's halo may stretch hundreds of thousands of light-years into space. It is not the product of a single collapse, but of accumulated gravity. Each swallowed galaxy contributed not only stars, but an invisible mass that deepened the Milky Way's gravitational well. This process continues today. As smaller dwarfs fall in, their dark matter is stripped and added to the halo, reinforcing the galaxy's dominance. The halo is therefore a living structure, still growing, still reshaping itself. Looking forward, this growth has a predictable endpoint. The Milky Way's largest future meal is already on a collision course. The Andromeda Galaxy, our nearest large neighbor, is approaching at hundreds of kilometers per second. In roughly 4 to 5 billion years, the two galaxies will collide. This will not be a head-on crash of stars, but a slow gravitational dance. Their disks will interpenetrate, tidal forces will stretch and warp both systems, and over time, they will merge into a single, larger galaxy. This future collision places the Milky Way's cannibalistic past in context. What we have done to smaller galaxies, Andromeda will do to us, and vice versa. Galactic cannibalism is not a moral judgment. It is a natural outcome of gravity acting over cosmic timescales. The future Milky Way will be a composite of both galaxies, just as the present Milky Way is a composite of many earlier ones. The stars of Gaia and Enceladus, Kraken, Sagittarius, and countless unnamed dwarfs will mingle with stars from Andromeda, forming a new system whose origins will be even harder to disentangle. From a human perspective, this story is unsettling and awe-inspiring at the same time. We tend to imagine galaxies as permanent homes, but the Milky Way is temporary, at least in its current form. It is an evolving structure, shaped by consumption, and destined to be consumed in turn. The atoms that make up Earth, life, and human bodies are already the product of this process. They were forged in stars from multiple galaxies, scattered by explosions, recycled through mergers, and assembled into new systems. When we say we are made of stardust, we undersell the truth. We are made of galactic debris, the end result of countless cosmic collisions. The Milky Way's growth through cannibalism also reframes its size. A galaxy that has eaten many others will naturally be larger, heavier, and more complex. Its extended halo, chaotic structure, and rich stellar population are not anomalies. They are the expected outcome of a long history of mergers. The revised size is therefore not surprising in hindsight. It is the footprint of a violent past written in stars and gravity. To look at the Milky Way today is to look at the aftermath of billions of years of accumulation. It is a survivor, a victor in countless gravitational contests, carrying within it the remains of galaxies that no longer exist as separate entities. And we are part of that story, orbiting quietly inside a system built from destruction, our existence made possible by the very process that erased so many others. This realization forces a deeper shift in how we think about identity at cosmic scales. If the Milky Way is a composite object, assembled from many galaxies over time, then the idea of a single, continuous lineage dissolves. There is no pure Milky Way ancestry. Every major component of the galaxy carries mixed origins. The halo is the most obvious example, but even the disk bears the marks of past accretion. Gas pulled in from mergers replenished star formation. Stars born from that gas inherited elements forged in alien environments. Over time, distinctions blurred. What began as foreign became native. Cannibalism did not merely add external pieces to the galaxy, it rewrote the galaxy from the inside out. This has consequences for how astronomers interpret the ages and histories of stars. A star's age does not necessarily reflect the age of the Milky Way region it currently inhabits. An ancient star in the halo may have formed in a small galaxy long before that galaxy was absorbed. A relatively young star in the disk may owe its existence to gas delivered by a merger billions of years earlier. The galaxy's timeline is therefore layered and non-linear. Events overlap. Causes and effects stretch across vast spans of time. In a Milky Way that grew quietly, history might be simpler. In a Milky Way that grew by eating others, history becomes tangled. Even the concept of galactic evolution changes. Instead of a smooth progression from youth to maturity, the Milky Way experienced punctuated growth. Long periods of relative calm were interrupted by violent encounters. Each encounter reshaped the system, altering its structure and future trajectory. This stop-and-start growth helps explain why the Milky Way exhibits properties that seem contradictory. It is both old and dynamically active. It contains ancient stars alongside regions of ongoing star formation. It shows signs of equilibrium in some regions and chaos in others. These contradictions are not flaws. They are signatures of a complex assembly process. Cannibalism also affects how astronomers interpret other galaxies. For a long time, the Milky Way was treated as a standard spiral, a template for understanding similar galaxies elsewhere. But if our galaxy's structure and mass are the result of an unusually rich merger history, then it may not be typical at all. Some spiral galaxies may have grown more quietly. Others may have experienced even more violent pasts. The diversity observed among galaxies may reflect differences in their cannibalistic histories as much as differences in initial conditions. This insight feeds back into cosmology. Large-scale simulations of the universe show that structure forms hierarchically. Small objects merge to form larger ones. The Milky Way is a local example of that process made visible. Its halo streams, thick disk, and chemical diversity are the observational counterparts of theoretical predictions. The revised size of the galaxy strengthens this connection. A galaxy as massive and extended as the Milky Way must have participated deeply in hierarchical growth. It could not have formed in isolation. In this sense, galactic cannibalism is not an optional detail. It is the central mechanism by which galaxies like ours come to exist. On a more personal level, this story reshapes humanity's relationship to the cosmos. We tend to imagine ourselves as inhabitants of a stable home, orbiting quietly within a familiar structure. But the Milky Way is not a peaceful island. It is a survivor of countless cosmic encounters, still in the process of change. The night sky looks calm because change happens on timescales far longer than human lives. Beneath that calm, gravity is constantly rearranging matter. Stars are drifting, streams are dissolving, satellites are falling in. The galaxy is still feeding. This perspective does not diminish our place in the universe. It deepens it. We are not merely residents of a galaxy. We are participants in a long chain of cosmic recycling. The atoms that make us were not just forged in stars. They were transported, mixed, and redistributed by galactic mergers. Our existence depends on a history of destruction as much as creation. In that sense, the Milky Way's cannibalism is not a dark footnote. It is the reason complex chemistry, rocky planets, and life itself became possible here. The galaxy we inhabit is large because it has consumed much. It is rich because it has inherited from many ancestors. And it continues to grow, quietly, relentlessly, as gravity draws new material into its expanding reach. Seen this way, the Milky Way's cannibalistic growth is not an exception, but a rule written into cosmic history. Galaxies are not isolated islands drifting serenely through space. They are nodes in a vast gravitational web, constantly tugging on one another. Over time, the stronger nodes grow stronger. The weaker ones are stretched, stripped, and absorbed. The Milky Way's present mass and size place it firmly among the winners of this process. Its extended halo, its crowded satellite system, and its layered stellar populations are all signatures of long-term dominance. A galaxy that did not eat would not become this large. This also clarifies why the Milky Way's outskirts look the way they do. The outer halo is not a quiet, primordial region left over from formation. It is an active archive. Each stellar stream is a chapter in the galaxy's feeding history. Some streams are young, sharply defined, still tracing the recent destruction of a dwarf galaxy. Others are ancient, smeared almost beyond recognition, their stars mixed so thoroughly that only subtle patterns in motion and chemistry betray their shared origin. As time passes, streams dissolve. The memory of individual mergers fades, but their mass remains. This gradual erasure is why the halo looks smooth at first glance, even though it is anything but. The smoothness is an illusion created by time. The galaxy's growth also explains why its mass estimates continued to rise as measurements improved. Each new tracer, each new satellite, each new stream added weight to the scale. The Milky Way did not suddenly gain mass when astronomers discovered Gaia Enceladus or Sagittarius. That mass was always there. We simply lacked the means to see its origins. As observational tools sharpened, the invisible history became legible. The galaxy's true weight emerged not from a single measurement, but from the convergence of many independent lines of evidence, all pointing toward a long, merger-driven past. This convergence is important because it reduces the likelihood that the revised picture is an artifact of method. Stellar motions, chemical signatures, satellite dynamics, and dark matter models all tell the same story. The Milky Way is large because it has accumulated the remains of many others. Its present form is inseparable from its appetite. The cannibalistic model also resolves a long-standing tension between theory and observation. Cosmological simulations predict that galaxies like the Milky Way should experience multiple significant mergers. For years, astronomers struggled to identify clear evidence of those events in our own galaxy. The disk appeared too intact. The halo seemed too smooth. Gaia changed that by revealing the subtle fingerprints that older data blurred away. The predicted mergers were there all along, hidden in the details. With the Milky Way now understood to be larger and more massive, the agreement between simulation and observation improves dramatically. Theory and reality align more closely than before. This alignment reinforces confidence in the broader framework of cosmic evolution. On even larger scales, the Milky Way's growth feeds into the story of the local group. Our galaxy does not exist alone. It shares its neighborhood with Andromeda, dozens of dwarf galaxies, and vast reservoirs of dark matter. The gravitational interplay among these components shapes their futures. The Milky Way's cannibalism affects not only itself, but the dynamics of the entire group. As it absorbs satellites, it alters the distribution of mass, changing orbital paths and future merger probabilities. The local group is a system in motion, and the Milky Way is one of its dominant actors. The coming collision with Andromeda will be the ultimate expression of this process. When the two galaxies merge, their halos will overlap long before their disks touch. Dark matter will interact first, reshaping gravitational fields on scales hundreds of thousands of light-years across. Only later will stars and gas respond, forming tidal tails, bridges, and shells. The final product will not resemble either galaxy as they exist today. It will be something new, built from the remains of both. In that future system, the distinction between Milky Way and Andromeda will be meaningless, just as the distinction between the Milky Way and Gaia Enceladus is meaningless today. Names fade. Mass persists. For life on Earth, this future collision is distant and largely irrelevant on practical timescales. The Sun will likely survive, orbiting within the merged galaxy under a changed sky. But conceptually, the collision completes the picture. The Milky Way's past, present, and future are all defined by cannibalism. It grew by eating others. It is still eating. And it will eventually be eaten in turn, absorbed into a larger structure. This is not a tragedy. It is the natural flow of matter under gravity. Understanding this flow reframes the galaxy's size as a dynamic quantity rather than a fixed number. The Milky Way is large because it has not finished growing. Its boundaries will continue to expand as long as there is mass to absorb and time for gravity to act. From this vantage point, the phrase, "we are made of alien matter," takes on its full meaning. It is not a poetic flourish. It is a literal description of our origin. The atoms in our bodies have been part of many stars, many planets, and many galaxies. They have crossed intergalactic space, been stripped from dying systems, and incorporated into new ones. The Milky Way is the latest vessel carrying them, not their first and not their last. To live inside this galaxy is to live inside a cosmic recycling process billions of years old. The revised size of the Milky Way does more than correct a measurement. It reveals the scale of that process. It shows how much has been consumed, how far the influence extends, and how deeply history is embedded in structure. The galaxy's vast halo, its chaotic disk, its immigrant stars, and its immense mass all tell the same story from different angles. The Milky Way is not simply big. It is the accumulated outcome of countless acts of gravitational conquest. And in that sense, our home is not just a place. It is a record of everything it has survived, absorbed, and become. After decades of indirect clues and partial reconstructions, the final push that forced the Milky Way's rewrite came from a new kind of observer, one that could see what had always been hidden. The James Webb Space Telescope did not invent the idea that the galaxy was larger than expected, but it removed the last excuses for doubt. Where earlier telescopes struggled against dust, distance, and faintness, Webb was designed to thrive. Operating primarily in the infrared, it sees through the thick veils of interstellar dust that block visible light. Regions once opaque became transparent. Structures once inferred became observable. The galaxy stopped hiding behind its own debris. This capability was crucial because many of the Milky Way's most important features lie buried in dust. The central regions, where mass is concentrated, were long obscured. So were vast stretches of the disk and inner halo. Webb pierced those regions cleanly, revealing dense star fields, extended stellar populations, and faint structures that optical surveys could only guess at. These observations filled in gaps that had plagued earlier models. The Milky Way's inner mass distribution became clearer. Its outer stellar populations became harder to dismiss as noise. The galaxy began to look continuous where it once appeared fragmented. Webb sensitivity also transformed the study of faint stars. Many of the stars that define the galaxy's true size are intrinsically dim. Red dwarfs, old halo stars, and diffuse stellar populations contribute little light individually, but they dominate in number. Webb's instruments can detect these stars at distances where previous telescopes simply failed. As a result, the stellar census expanded outward. Regions once thought sparsely populated were revealed to host coherent stellar structures. The galaxy's outskirts became populated, not empty. This alone pushed size estimates upward. But Webb's role went beyond counting stars. It also provided new ways to measure mass directly. One of the most powerful tools in modern astronomy is gravitational lensing, the bending of light by mass. When light from distant galaxies passes through the Milky Way's halo, its path is subtly distorted. These distortions are tiny, but measurable with precise instruments. Webb's resolution and stability allowed astronomers to detect lensing effects caused by the Milky Way itself, not just massive clusters far away. This was a critical confirmation. Lensing does not care what matter is made of. It responds only to gravity. When lensing measurements matched the mass required by stellar streams and satellite motions, skepticism collapsed. The dark matter halo was not a theoretical convenience. It was physically present, massive, and extended. Webb also sharpened comparisons between the Milky Way and other galaxies. By observing distant spirals in unprecedented detail, astronomers could place our galaxy in context. Many galaxies similar in mass and structure showed extended halos, faint outer disks, and complex substructure. The Milky Way no longer looked anomalous. It looked typical for a galaxy of its mass. The earlier, smaller estimates began to stand out as the anomaly. This comparative approach mattered because science is conservative by design. Extraordinary claims require convergence from multiple directions. Webb helped provide that convergence. Independent lines of evidence, using different methods and different targets, all pointed toward the same conclusion. The Milky Way had been underestimated. As Webb's data accumulated, resistance softened. Debates that once hinged on model assumptions shifted toward refinement rather than rejection. Astronomers no longer argued over whether the galaxy was larger, but by how much. The language changed. Papers stopped hedging. Reviews began to acknowledge that textbook values were outdated. Educational materials lagged behind, but the consensus within the field moved decisively. The idea of a 100,000 light-year Milky Way quietly expired. This shift did not happen overnight. Science rarely works that way. But Webb accelerated a process that might otherwise have taken decades. By removing observational blind spots, it forced theorists and observers to reconcile their models with reality. When the dust was stripped away, both literally and figuratively, the galaxy revealed itself as larger, heavier, and more complex than the simplified diagrams of the past. The rewrite was no longer optional. It was required. And with Webb continuing to operate, the process is still ongoing. The Milky Way's story is not finished being told, but one chapter is now closed. The old picture, comfortable and familiar, has been replaced by something truer. The galaxy we live in is not the one we were taught about. And thanks to Webb, that fact can no longer be ignored. Once the Milky Way's true scale was acknowledged, the consequences did not stop at galactic astronomy. They propagated outward into cosmology itself, touching questions about how the universe expands, how fast it does so, and why that expansion behaves the way it does. Galaxies are not just islands of stars. They are the scaffolding on which cosmological measurements are built. Change the properties of galaxies, and you subtly change the foundation of the universe model. A larger, more massive Milky Way may seem parochial, but it forces a reconsideration of assumptions used far beyond our local neighborhood. Many cosmological measurements rely on calibrations tied to galaxies like ours. When astronomers estimate distances across the universe, they use standard candles and standard rulers, objects whose intrinsic properties are assumed to be well understood. Cepheid variable stars, supernovae, and other distance indicators are often calibrated using nearby galaxies. If the structure, mass distribution, or stellar populations of those galaxies were mischaracterized, the calibration inherits that bias. A Milky Way that is twice as large and significantly more massive than assumed implies differences in stellar environments, metallicity distributions, and gravitational effects that ripple through these calibrations. Individually, these differences are small. Collectively, they matter. This feeds directly into one of the most persistent problems in modern cosmology: the Hubble tension. Measurements of the universe's expansion rate disagree depending on how they are made. Observations of the early universe using the cosmic microwave background yield one value. Measurements based on nearby galaxies and supernovae yield a higher one. The discrepancy is not trivial. It is large enough that it cannot be easily dismissed as experimental error. For years, cosmologists have debated whether the tension signals new physics or unrecognized systematics. A revision in galactic structure does not solve the tension outright, but it changes the context. If galaxies like the Milky Way are more massive and extended, then local gravitational environments may influence distance measurements more than previously accounted for. Gravitational potentials affect light propagation. Stellar populations affect standard candles. Dark matter halos alter local expansion flows. These effects were often treated as secondary. A larger Milky Way suggests they deserve more weight. In some models, accounting for stronger local gravitational influence shifts inferred distances slightly, nudging expansion rate estimates. In others, it amplifies the discrepancy, sharpening the tension rather than easing it. Either outcome is significant. It means the universe is less forgiving of simplifying assumptions than hoped. The fallout extends further. Dark energy, the mysterious driver of cosmic acceleration, is inferred from how galaxies and clusters behave on large scales. If galaxies are systematically more massive, then the balance between matter and dark energy changes. Matter resists expansion. Dark energy accelerates it. The precise ratio between the two determines the universe's fate. Underestimate galactic mass, and you underestimate the matter content of the universe. Overestimate dark energy by comparison. Correcting galaxy masses upward shifts that balance. The effect is subtle, but cosmology lives in subtleties. When data from billions of galaxies are combined, small corrections accumulate into meaningful shifts. This is especially relevant when comparing observations across cosmic time. Early galaxies, observed when the universe was young, are often interpreted through models built from nearby examples. If our understanding of local galaxies was incomplete, then inferences about distant ones inherit that incompleteness. This feeds into debates about whether dark energy has remained constant over time or evolved. Some observations hint that cosmic acceleration may not be perfectly uniform. Others suggest it is. A universe built on slightly misjudged galactic masses muddies that picture. The Milky Way's revision becomes part of a larger pattern. Over the past decade, cosmology has been repeatedly confronted with tensions. Expansion rates disagree. Early galaxies appear too massive, too evolved, too soon. Large-scale structures seem slightly misaligned with predictions. None of these issues alone overturn the standard model, but together they create pressure. A larger Milky Way fits into this narrative. It is another reminder that the universe may be less tidy than our equations prefer. Constants we treat as fixed may be effective descriptions rather than fundamental truths. Dark energy may not be a single, unchanging property of space. It may interact with matter in ways we do not yet understand. Alternatively, gravity itself may behave differently on large scales. These ideas remain speculative, but they gain traction as observational cracks accumulate. The revised galaxy size does not demand a new cosmology, but it erodes confidence in the idea that everything is already accounted for. It reinforces the sense that our models are approximations, not final answers. This realization reshapes scientific humility. For decades, the standard cosmological model has been remarkably successful. It explains the cosmic microwave background, large-scale structure, and the overall expansion history of the universe with impressive precision. But success can breed complacency. The Milky Way's mismeasurement is a reminder that even foundational quantities can be wrong by factors of 2 without immediately breaking the model. The universe tolerated our mistakes longer than we realized. That tolerance should not be mistaken for correctness. A larger Milky Way invites cosmologists to revisit assumptions at every scale. How do local environments influence global measurements? How uniform is dark energy, really? How sensitive are our conclusions to hidden mass and unseen structure? These questions do not undermine cosmology. They strengthen it by forcing rigor. The universe has not changed. Our understanding has. And as with the galaxy itself, expanding the scale of what we know reveals not closure, but new space for uncertainty. Even after all these revisions, one truth remains unavoidable. We still do not know exactly how big the Milky Way is. The galaxy's halo fades so gradually into space that any attempt to define a final boundary depends on where one chooses to stop measuring. Gravity weakens with distance, but it never shuts off cleanly. Dark matter density drops, but it does not abruptly vanish. Stars become rarer, but they do not suddenly disappear. As a result, every size estimate carries uncertainty, not because astronomers are careless, but because nature refuses to draw sharp lines. The current figures, 200,000 light-years, 300,000, even 400,000 in some models, are best understood as ranges rather than answers. The true edge, if it exists at all, is smeared across vast distances. This uncertainty is not a failure. It is a reflection of how galaxies actually work. The Milky Way is not an object with a wall around it. It is a gravitational gradient embedded in a larger cosmic environment. One of the most persistent puzzles tied to this uncertainty is the so-called missing satellites problem. Cosmological simulations predict that galaxies like the Milky Way should be surrounded by hundreds, perhaps thousands, of small dwarf galaxies. Yet only a few dozen have been observed so far. Where are the rest? Some may be too faint to detect with current instruments, their stars spread thinly across the sky. Others may contain little to no star formation at all, composed almost entirely of dark matter. If so, they would be nearly invisible except through their gravitational effects. A larger Milky Way exacerbates this problem. A more massive halo should host more satellites, not fewer. The discrepancy suggests either that many satellites remain undiscovered, or that our understanding of dark matter and galaxy formation is incomplete. Stellar streams offer hints. Gaps and distortions in streams may betray the presence of dark subhalos, invisible clumps of mass passing nearby. These indirect detections suggest that many satellites exist without stars, lurking unseen in the halo. Confirming this requires more sensitive measurements. This is where future observatories come in. The next generation of telescopes is designed specifically to address these blind spots. The Nancy Grace Roman Space Telescope will survey large areas of the sky with exquisite precision, detecting faint stars and subtle distortions over enormous volumes. Roman's wide-field infrared vision will complement Gaia, extending detailed mapping deeper into the halo and farther from the galactic centers. It will be particularly effective at finding low-surface brightness structures, the ghostly remnants of ancient mergers, and the faint signatures of elusive satellites. By tracing these features, astronomers hope to refine the shape and extent of the dark matter halo with unprecedented accuracy. On the ground, extremely large telescopes will push resolution and sensitivity to new extremes. Facilities like the Extremely Large Telescope will be capable of resolving individual stars in distant, faint systems that are currently blurred into noise. These instruments will allow direct measurement of stellar motions in the outer halo, tightening constraints on mass and escape velocity. With enough data points, astronomers can better determine where the Milky Way's gravitational grip truly weakens. Even then, the answer may remain probabilistic rather than definitive, but the range of uncertainty will shrink. Future measurements will also clarify the role of dark matter itself. Different dark matter models predict different halo shapes and substructure distributions. A smooth, particle-like. Dark matter halo behaves differently from one composed of clumps or exhibiting self-interactions. By mapping stellar streams and satellite motions in detail, astronomers can test these models directly. The Milky Way becomes not just an object of study, but an experiment, a nearby laboratory for fundamental physics. At the same time, unanswered questions about the galaxy's past continue to surface. How many major mergers did the Milky Way experience? Were Gaia, Enceladus, and Kraken the largest? Or are there others still hidden in the data? How much of the thick disk formed internally, and how much was produced by collisions? These questions tie directly into size estimates. Each merger adds mass, extends the halo, and reshapes structure. Without a complete merger inventory, the galaxy's growth curve remains uncertain. Even the future holds unknowns. The interaction with Andromeda is inevitable, but its details depend on halo size and shape. A larger halo implies earlier interaction, stronger tidal effects, and a more complex merger. Understanding the Milky Way's present halo is essential for predicting its future. In this sense, uncertainty is not a temporary inconvenience. It is a permanent feature of studying a system this large. As tools improve, answers sharpen, but new questions emerge. The Milky Way's revised size has not closed a chapter. It has opened one. It has shifted astronomy from asking how big the galaxy is to asking how galaxies behave when they grow without clear limits. That question reaches beyond our home and into the broader universe, and it ensures that even with the most powerful telescopes yet to come, the Milky Way will continue to surprise us. In the end, the most important lesson from the Milky Way's revision is not a number. It is a shift in perspective. We set out to measure the size of our galaxy and discovered instead the limits of our assumptions. The Milky Way did not suddenly grow. Our understanding did. What once seemed like a well-mapped spiral now reveals itself as a vast, fading region of influence, shaped by dark matter, mergers, and time. There is no final edge to point to with certainty, only a gradual thinning where gravity loosens its grip and space takes over. This does not mean science failed. It means science worked exactly as it should. Each new instrument stripped away another layer of illusion, forcing older ideas to yield to better evidence. The galaxy became messier, larger, and more complex, not because nature changed, but because we learned how to see it more clearly. There is humility in that realization. We live deep inside a structure so immense that light takes hundreds of thousands of years to cross it, built from the remains of galaxies that no longer exist as separate things. Even our own atoms carry that history. The Milky Way is not a backdrop. It is an ongoing process, and we are part of it. The final synthesis is simple and unsettling. There may never be a single clean answer to how big our galaxy is, because the question itself assumes boundaries that nature does not respect. What we can say is this: our home is far larger than we were taught, far older than we imagine, and still unfinished. And in realizing that, we gain something more valuable than certainty. We gain a clearer sense of where we stand in a universe that continues to exceed our expectations. And that is where this journey truly ends, not with a measurement, but with a realization. The Milky Way is not a diagram, a boundary, or a finished object. It is a vast, evolving system whose true scale resists simplification. For generations, we believed we understood our place in the cosmos because the maps felt complete. Now we know those maps were sketches, drawn from the inside, limited by what we could see at the time. As our tools improved, the galaxy revealed more of itself, and with each revelation, certainty gave way to humility. We are not standing at the center of a neatly defined spiral. We are orbiting within a gravitational domain that stretches far beyond intuition, built from the remnants of countless galaxies and still shaped by forces we only partially grasp. This does not make our place smaller. It makes it more profound. To exist within something so immense, so old, and so unfinished is to be part of an ongoing story rather than a completed one. The Milky Way reminds us that knowledge is provisional, that understanding grows by revision, and that even our cosmic home is larger, stranger, and more dynamic than we were ever taught. In the end, the galaxy did not betray us by being bigger than expected. It invited us to see further, think deeper, and accept that wonder does not shrink as answers arrive. It expands,